Welcome to lecture number 7. Let's start up piano as usual. In the last lecture we created a generic 250-seater completely from scratch. Then we did some parametric adjustments, ran another optimization and ended up with a good approximation to the Boeing 787. I'm calling this our lecture 6 model. The top plane in this list is our reference 787 V14 file from Piano's current aircraft database. We have been using this as a reliable baseline that reflects closely the 2014 ACAP characteristics. In this session I will refine or calibrate our lecture 6 model to line it up more accurately with the V14 baseline. And after that I will rework it into the latest stretched version of the 787, namely the 787-10. But before all that, I want to make a small digression into optimization and briefly discuss a couple of relevant points. In lecture 6 we chose to use MTOW as the optimization objective that we wanted to minimize, but of course there are alternatives. This slide shows an older example study that looked at some alternative optimizations based on different objectives. Now, talking about design decisions and optimization philosophies opens up a gigantic Pandora's box, but for large long-range aircraft such as this, simply minimizing the MTOW is likely to give a well-balanced design solution. And that is what we already discovered in our case with the lecture 6 plane. Here we have some results of optimizing for minimum MTOW, minimum fuel, minimum cash cost and minimum DOC. You can go through the numbers if you like. The minimum MTOW solution is essentially the same as the model that we derived, and minimum DOC turns out to be very close to that as well, although that will depend on just how the DOC is defined. The high aspect ratio solutions are minimum fuel and minimum cash cost. These come with a high penalty on empty weight and MTOW. They would also add structural complexity and aeroelastic risks for a fairly modest fuel advantage. Anyhow, no matter what objective function a designer chooses to minimize, judgments are necessarily involved. Design philosophies and solutions are never unique. Next, this is another exercise from some time ago, showing the effects of using different engine models. Without going into the details of engine characteristics, which you can always find in the Piano website or the built-in user's guide, the important thing to remember is that engines are generic normalized datasets that can be scaled to arbitrary thrust and SFC levels. We have here 3 such distinct rubber engine models from independent sources. These were used at different times during the evolution of Piano models of the 787, going back to 2004 and prior to that. None of them refers to any particular engine make. In this exercise, all 3 generic engines were adjusted to a common nominal point, specifically an SFC of 0.523 at a typical cruise thrust of around 12,000 pounds, Mach 0.85, flight level 360. An aircraft sizing optimization was then carried out using each engine in turn. As you will see if you read through the numbers, there is little difference between the 3 final aircraft configurations, which is a good thing and gives us confidence in such rubber engine representations. Picking a baseline value for SFC like the one I've just given is a process. That means making judgments informed by expert individuals or by consensus views from inside the industry. As always, choices made in Piano models do not reflect the position of any specific party. It's interesting to look back at the history of SFC levels used in Piano models at different times. There are some dated examples in the piano.aero website, and this is the initial 7E7 position around 2004 and even before that. This is a published Piano model that was released in 2005. Over more than a decade, SFC expectations changed very little, despite significant variations in performance claims for the 787 during its development. Good consistency is also seen in Piano's predictions of typical aerodynamic levels. In contrast, certification weights and OEW expectations are much less likely to survive the bumpy ride from preliminary claims to entry into service. And this happened to the 7E7 or 787 project as well, pretty much as expected. Now let's get started with some calibration. Remember that the Lecture 6 model was a design exercise. We picked simple specification targets, ran an optimization, and got remarkably close to the 787 in less than an hour. Now, for calibration purposes, we want to set actual 787 numbers, or at least those that are in the public domain, like span and certification weights. We could be methodical and try to refine as many parameters as we can as much as possible. For example, we could easily set a more exact tail geometry. But the overall impact of that would be small, and we won't do it here. Instead, we will focus on just a small selection of the most relevant parameters. Let's load the V14 and pick out some of these key settings. Looking at the actual geometry of the V14, some numbers to remember. The overall span, 197.25 feet. Boeing windpress area for the wing, 3880 square feet. Fuel capacity, a purely geometric quantity, 33,340 US gallons. Certification weights, MTOW 502,500 pounds, maximum landing weight 380,000 pounds, maximum zero fuel weight 355,000. And OEW, not a certification weight, but as given in the ACAP, 259,500 pounds. By the way, you may notice that sometimes units seem to swap around at random. I'm simply using keyboard shortcuts to do that. Let's remind ourselves of the V14 range as well, 7725 nautical miles, and that is with 242 passengers. In terms of engine characteristics, notice that the V14 uses the high BPR 10s X1 model, and the Lecture 6 plane that we will look at in a moment uses a different engine. For the V14, the nominal available sea level static thrust is 72,000 pounds, and we can look at our reference SFC point at 36,000 feet, Mach 0.85 and 12,000 pounds of thrust. Our SFC is 0.532. Finally, let's look at the overall aerodynamics. Peak lift to drag ratio around 20.5 at Mach 0.85. Ignore the kink from the aeroelasticity adjustment. Now, I'm personally confident that this V14 drag polar is a very good approximation to the true aerodynamics of the 787, but as always it remains strictly a piano assessment. For our purposes, I will treat these aerodynamic levels as our target, and I will adjust the Lecture 6 plane to get close to this basis. So these are all the characteristics we'll be working with. We can now load the Lecture 6 model and start implementing the necessary changes. I'll be toggling between metric or imperial. We are finished with sizing, and so we won't need nacelle scaling anymore. Turn it off. Also, we might as well keep the tail geometry fixed as it stands at the moment. We will set the wing geometry. Boeing windpress area, use it as a reference in reports. 3880 square feet. And overall span 197.25 feet. We'll keep the rest of the wing geometry the same, so we can now set the fuel capacity as well. 33340 US gallons. Set the weights. MTOW 502,500. MZFW 355,000. Maximum landing weight 380,000. Freezing the OW at 259,500 pounds per the 2014 ACAP. The engine model that the Lecture 6 plane uses is the high BPR Noughts Advanced, and we will not change that. We will simply adjust the thrust level and the SFC. Our reference thrust at the end of the optimization was 70,860 pounds, and I'm going to apply a user factor on takeoff rating of 72,000, which is our required available thrust level, divided by 70860.4, roughly a 1.6% increase. And looking at our current SFC point performance under the same conditions, flight level 360, Mach 0.85, 12,000 pounds of thrust, we have an SFC of 0.523 essentially. So to bring it to the required level, I will apply a user factor on SFC of 0.532 divided by 0.523. Looking at engine point performance again, we do have an SFC of essentially 0.532. This is how our aircraft looks. Let's look at the range after the changes that we have made. 7,661 nautical miles. And we will aim to restore 7,725 nautical miles by the time we complete all our changes. In between weights and aerodynamics, let's now consider aeroelasticity. Without detailed prior knowledge, our rationale is going to be that we can reasonably expect the combined trailing edge variable camber and load alleviation systems and their associated software to use conservative early settings in order to reduce structural loads at the highest weights, at least until enough operational experience has been gained. There are some indications of early drag levels that hint at as much as a 5% potential penalty at the highest weights. Near the start of the cruise, we might be at around 220 tons, but the penalty then drops very rapidly, reducing down to essentially nothing by around 200 tons. So let us implement a rough adjustment with the user elastic drive curve. And I will say at 200 tons, 200,000 kilograms, the factor is 1. And at 220,000 it's 1.05. Going down by 1/4 of the distance to 215,000, I will reduce the factor to a half of that, 1.025. And halfway between the weights, 210,000 kilograms, I will just put 1.01. So this is a rough estimate for an adjustment. And if we run our range again, we are down to 7,611 nautical miles. So we have lost, in essence, 50 nautical miles. Not too much, because the effect is only applied at the very highest weights. Next, we can tweak the aerodynamics. We are using the RR adjustable method, and there is an empirical technology parameter that can be used within that method, this one here. It has a value between 0.1 and 0.15 normally, and aerofoils that are highly optimized for the cruise can show increased sensitivity. This would apply for the 787, so I will increase the value to 0.15. Looking at the user adjust CLCD curve, which largely depends on aerofoil characteristics, I'm going to shift the whole curve a little bit to the right by adding 0.05 to all the CLs. Note, by the way, these adjustments are based on trapezoidal area. I will also make the whole shape slightly more peaky by changing the drag increments on either side of the minimum from 2 counts to 5 counts. So these are purely empirical refinements to get us close to the V14 aerodynamics. We'll reduce our windscreen drag to 0. And we'll also make a small change to our minimum static margin from 5% down to 3%. And let's now check the range again. So we are back up to 7699 nautical miles, pretty close to our original range. I could continue with minor parameter adjustments, but that is close enough, and I will apply a user factor on the total drag now, roughly in proportion to the ranges that we are at and that we expect. So this factor will be 7699 divided by 7725, about 0.997. And looking at our range report, we have now reached 7725 nautical miles. If we look at our drag polar, we are indeed where we expect. You can see the elasticity effect, and the overall polar turns out to be a pretty good match to the V14 polar that we just looked at a moment ago, certainly for combinations of Mach and CL that are operationally relevant. Of course, there can be no complete certainties in several of our choices, and deciding these kind of adjustments assumes some knowledge of characteristics together with some trial and error. Accumulated experience becomes applicable to other similar aircraft in the database, and that is the nature of calibration in piano or in any tool. Let's now save our plane, and I will call it our Lecture 7 design, and compare it with the V14. V14 and our Lecture 7 model. So we have the same span, 60.1 meters, 360 square meters for the wing areas. Thrusts are the same, 72,000 pounds. All the weights are the same, and the fuel capacity the same as well. Our design range is the same, and our block fuel burns are roughly 174,300 pounds and 174,700 pounds. And our payload ranges for the two aircraft are virtually identical. So we have now managed to get very close to the Boeing 787 V14 model. Remember that at the end of Lecture 2 we carefully compared the V14 model against the November 2014 ACAP data, and if we were to repeat all that using our Lecture 7 model, we would basically be just as close. Even so, it is worth noting that there are still many differences in parameters between the Lecture 7 and V14 files, and these go as far as the use of different engine models. We can compare the files directly. So you have here a comprehensive list of all the parameter differences. Yet, despite these differences, in terms of performance, the two planes are virtually indistinguishable after our calibration. This kind of exercise can become very effective as designs mature and our knowledge increases. So we now have a very good calibrated model, and crucially, it remains fully adjustable. Let's reload it. And for example, we can increase the OEW by 5,000 pounds, which will match the December 2015 ACAP now. add 5,000 pounds. And we can fly the aircraft with our 242 passengers again. At MTOW, but let us assume that the passengers now weigh 220 pounds each. So we have 242 times 220 as our payload. We get a range of 7,336 nautical miles. Pick a different set of flight levels, RVSM eastbound. Flight again, and we get 7,348 nautical miles. Let's say 7,350, recognizably near to common quotes. Any range quote is meaningless unless all its assumptions are clearly listed. But piano numbers are inherently explicit about reserves, weights, and everything else that is needed. Now, let us use our latest model of the Dash 8 to generate a different variant of the 787. I will skip the Dash 9 and move directly to the longest stretch variant, which is the 787-10. The development of the Dash 10 took several years and relied on experience gained from both the Dash 8 and the Dash 9. For example, one judgment made by Boeing was to not include the original planned wing extension, which kind of relates to what I said earlier about span in the context of optimization. Many unknown details about trim and balance and tail geometries can influence the best choice of wing location, or in other words, the split between fore and aft fuselage plugs. We will simply take the published gross changes in geometry and certification weights directly from the Dash 10 specifications in the March 2018 ACAP. So I will now implement these changes. First, let's free up the wing location. Set our passenger count to 330 and increase our mid-fuselage length by 11.5 meters. Some secondary settings we just can't know for sure. For example, with such a long fuselage, we might be a little bit conservative with CG and loading arrangements and reset our nominal static margin back to 5%. And let's look at the aircraft. The wing location is set by the wing apex parameter, which reflects this point here. At the moment, the wing apex fuselage fraction is 0.333, and I will set it to about 0.34, which is roughly what you get from the drawing. And piano tells me that in doing so, I have to release the fixed equipment CG fraction. Otherwise the problem is overconstrained. So I will do so, and I can redraw the aircraft. And we now have the geometry that we needed. Let us set the certification weights. MTOW is given us 560,000 pounds. MZFW 425,000. And maximum landing weight 445,000. Individual known values for OEW seem to vary between, say, 299,000 pounds and 306,000 pounds. So I will nominally set an OEW of 300,000 pounds exactly. For convenience, and because this also happens to line up with the start of the payload range diagram that is given in the March 2018 ACAP. What about the engine? Although this is not clearly defined, we can take the stated engine thrust, which is 76,000 pounds, and assume it refers to Boeing equivalent thrust, or BET. BET is calculated as net available thrust at Mach 0.25 divided by 1.255, and you can see this definition in the user guide. Its value is shown here. So at the moment BET is 69,012 pounds. I will go into the engine palette, take the existing user factor on takeoff rating, multiply it by 76,000 and divide it by 69,012. And now our BET thrust is indeed 76,000 pounds. We'll treat this thrust increase as a simple throttle push for the takeoff rating alone without making any changes to the cruise or climb ratings. What about aeroelasticity? Clearly we don't want to use the adjustments that we made for the Dash 8, as our weights are now very different. We clearly expect much more experience to be incorporated in the Dash 10 with structural modifications and or software tweaks for the trailing edge variable camber and load alleviation systems. So I will apply no adjustment at the lowest weights, let's say roughly 135 tons, and just the 1% adjustment at the highest weight, let's say roughly 250 tons. I will finish off with a couple of small arbitrary tweaks, only intended to give a near-perfect match in performance. I will nudge our overall drag factor, which is currently roughly 0.997, up to 1.01, so that's just over 1% adjustment. And I could have instead included some of that adjustment in aeroelasticity. And lastly, although we are not focusing much on field performance, I'll add a small increase to the takeoff and landing CL maxes, and I will improve these by about 3%. User factors on the CL max for the landing and takeoff, 1.03. The thinking being that we might expect some increased confidence with smaller aerodynamic refinements or reprogrammed flap or other control surface settings for this later model. Let's look at takeoff in field performance. The ACAP gives around 9,600 feet of takeoff field length. We're at 9,674, and around 6,100 feet for the landing field length, which is also now very near. Let's take a look at the range calculations then. But Piano tells us that it can't quite get to 36,000 feet. And if I look at our range modes, you may remember that we restricted our altitudes to start at flight level 360 in the previous definition. So we can now release that and allow all westbound RVSM flight levels. Try again. So we now get a range of 6,537 nautical miles with a payload of 31.4 tons or 69,300 pounds. So we will now save this as our Lecture 7 787-10 model. Run our payload range. And we can compare this with the March 2018 ACAP. This is the Piano payload range that we just produced, and overlaying it on the ACAP picture we get an exact match at the boundary. We will pick some easy to read spots inside the payload range diagram. I've marked some obvious ones here. These are the numbers that you can pick from those points, and I can run our Dash 10 model at those numbers. So we have At the takeoff weight of 560,000 pounds and the payload of 70,000 pounds, we expect 6,500 nautical miles. This is what piano gives. At 460,000 pounds takeoff weight and the payload of 10,000 pounds, we expect 6,000 nautical miles. Piano gives 5,994. At the same MTOW with the payload of 40,000 pounds, we expect 4,500. Piano gives 4,503. At a takeoff weight of 520,000 pounds and a payload of 110,000, we expect 3,500 nautical miles. And that's what we get. At a takeoff weight of 440,000 with a payload of 100,000, we expect 1,000 nautical miles, 1,014. Takeoff weight of 380,000 and a payload of 55,000. We expect 500 nautical miles, 497. So once again, we have a very close alignment of the piano mission assessments with the nominal performance of the actual 787-10. We have now encapsulated these accuracies in a tiny plain file containing less than 100 parameters. This shows the cumulative power of calibration. In fact, there are not many differences between the definition files for our -8 and -10. If we compare the files, these are essentially the changes that we have made. We can compare the two planes. Lecture 7-10 and Lecture 7-8. As always, we can adjust our new -10 model to any weight standards or reserves or operational choices. Let's load it. Reset our OAW to, let's say, 299,000. And if we assume that our 330 passengers now weigh 220 pounds each, we get a range of 6,434 nautical miles. And you might see similar numbers in common performance quotes given without any background. To conclude, we are now in a position to look at things like transport efficiencies and fuel burns and, of course, CO2 emissions. And we can do it in great detail, just as we did during lectures 2 and 3. One thing we can produce in a few tens of seconds is this picture. If you multiply the y-axis of this picture by 3.16, you will know the direct CO2 emissions of this very good model of the 787-10 over any mission range and with any payload. I hope this has shown you how piano models can quantify CO2 emissions accurately. They're adjustable at all levels of technical detail, they're explicit about all assumptions and operational scenarios, and they can be tested by any analyst. They provide transparent apples-to-apples comparisons. This is a core capability and a necessary precondition for any global consensus action on aviation carbon emissions. So I will finish this analysis of the 787 here. In the next session, we will go back to our generic 250-seater design and start again along a different path that will lead us to a model of the A350.